Okay, so hi everyone. In this video, I am going to discuss about the divide and conquer algorithms and recurrence relations. So when we say divide and conquer, so this is a class of algorithmic techniques that solves problems in three different steps: divide, conquer, and then combine. So what are these three different steps? So first is the divide. In this step, we are breaking the problem into subproblems that are themselves smaller instances of the same type of problem. And when we say conquer, we are recursively solving the subproblems. So many recursive algorithms take a problem with a given input, and that given input will be divided into one or more smaller problems. So this reduction is successively applied until the solutions of the smaller problems can be found quickly. So essentially, uh, you can compare it with the way we manage a task or we solve a certain problem. We don't actually just solve one problem on its own. That will be heavier to do, right? So what we do is that certain problem will be divided into smaller tasks such that these tasks are easier to solve and are more achievable. Okay, so after solving the subproblems, so we appropriately combine or merge the answers to form the original problem's answer. So at the tail end of recursion, or that is the base case, and the subproblems are so small that they can be solved outright or trivially. And how does it improve on the natural brute force approach? So the brute force approach is naive, obvious, as well as not sophisticated. And in most cases, this will be taking up a lot of time and also taking up a lot of memory to implement. Okay, so that's why we use other solutions like the divide and conquer. And with this divide and conquer, we are able to reduce the running time to a lower polynomial. So simply said, what this means is we are just making the algorithm run faster so we can immediately get a solution, or we can also reduce the space in the memory that the algorithm is using. Okay, so these are some examples: the merge sort, the quick sort, and then the binary search. So while the merge and the quick sort are making use of the three steps, which are the divide, conquer, and the combine, the binary search does not have any combined step. So later I will discuss each of these algorithms. So let's start with the merge sort. So in the merge sort, we have a list of numbers here that are unsorted. And our end goal here is to be able to sort these numbers from the smallest to the largest number. So in the merge sort, what we do is to recursively divide this list into halves until um, we break it up into individual numbers. So first is we divide this by 2. So we have 2, 4, 1, 6, and then 8, 5, 7, 3. And then we divide this list again into 2. So we have 2 and 4, and then 1 and 6. Similarly, for the right list, we also divide it by 2. So later we'll show that. But anyway, for this, we will divide this pair into 2 also, giving us the individual numbers 2 and 4, and then 1 and 6. And going back to the right, so we divide 8573 into 85 and 73. And we divide 85 into 8 and 5, and 73 into 7 and 3. Okay, so we are done with the division part. So next would be the conquer na part. So we will start with the individual na elements and then sort it. So this is already sorted. And then this 1, 6, so is 1 less than 6. So it is true. So this is already sorted. And this 2, 4, and 1, 6 again, we are going to sort sort the list again. So we will have 1, 2, 4, 6. So do you see the pattern here? So after dividing it, and then we are going to solve or sort the smaller the list. Okay? So Yeah. And then here also, we also compare the two numbers and then swapping it if the right side is bigger than the left side. And then we also combine here the solution. So we have 3, 5, 7, 8. So we will have this two sorted na list, 1, 2, 4, 6, and 3, 5, 7, 8. And later, we are going to combine the solutions again into the final na solution. All right? So if you want to know more about merge sort, so you can watch this fun YouTube video. So in a nutshell, so what we do is to break the problem into several problems similar to the original, but only smaller in size. And we are solving the problems or the sub-problems recursively. And later, we are combining these solutions to create solution to the original problem. So what about the quicksort? Let us move on to another example. So quicksort also uses divide and conquer na technique. And what we have here is a variable or a pivot that is used to divide the array into two halves. So like the merge sort, but different in some way. You will see later, in such a way that the elements on the left half are smaller than the pivot or the pivot, and the elements on the right are greater than the pivot. So the steps that we have to recursively follow are this. So we first find the pivot that divides the array into two halves, and then we quicksort on the left half, and then we quicksort on the right half. So essentially, we have this list of elements, okay, that are unsorted. So 7, 2, 1, 6, 8, 5, 1, 3. And it was said earlier that we have some pivot, okay? We have some pivot. And in this case, we are choosing the last element as our pivot for now. And what we are going to do, or the goal of this quick sort, is to partition from the title itself, quick sort partitioning, is that we partition this array such that this pivot will be able to find its place. Okay, so in this case, the place of this pivot is between this list and then this smaller na list. And you can see that all the elements on the left of the pivot are smaller than the pivot, which is 4. So 2, 1, and 3, they are values that are smaller than 4. And all values on the right of the pivot are on the other hand, larger than the pivot, which is equal to 4. Okay, so this is the goal of the quicksort na partitioning. And then later, we are going to recursively solve the problem. And since we already have found this place, so we will perform quicksort on the left half and the right half also. So we are basically going to repeat the same process on the left as well as on the right. Okay, so we will see that more of that. So assuming that we have this list again, and the pivot has already found its place. So we are going to perform quicksort here and then quicksort on the right half also. So now, performing quicksort on the left half, which composes of 2, 1, and 3. So we will assume also that 3, the last element will be our starting pivot, and we will find its place. And for the right half, we will also assume that the last element, which is 6, will be our pivot. Okay, so let us quickly explain how this works. All right, so as I mentioned, we can set the last element as the pivot, but for now, actually there are some ways on how we can select the pivot, but for now, let us settle on selecting the last na element. Okay, so we have two variables here, the p index, and then we also have the c na variable. So let us start with the p index. So the p index is the pivot na index. So I have mentioned earlier that, right, that we are going to look for the proper place of the pivot, which is, let's say, this 4. Okay, so this p index, so you can also call it like the potential index. Okay, so that is the place where we are going to place the 4, right? And we have a C, or the current value, that iterates from the left to the right na element. So iterates from here until it reaches the pivot value, which is 4. Okay, so what we are going to do is to compare the current na value C with the pivot. So is C less than or equal to pivot? Since no, since you can see that 7 is greater than 4, so this is not true. So we will do nothing, and we move C one step to the right. Okay, and the P index remains here. Okay, and now is the C less than, or the current value C less than or equal to the pivot? In this case, it is yes, because 2 is less than 4. So what we are going to do is to swap the current value C with the P index. So we swap this. So the 2 is now on the other side and 7 on the right side. And we also increase or increment P index by 1. So P index is now here. And we also increment C. So C moves one step to the right also. Now, is the current value 1 less than or equal to the pivot? In this case, it is also true. So what we are going to do again is we are going to swap this current value C with the P index. Okay, swap, and then increment P index. So P index is now 2, and C will also be incremented, and C is now has moved one step to the right. Okay, now let us compare. Is the C less than or equal to the pivot? No, because we can see here that C is greater than 4. So what we are going to do is move. We do nothing. So actually, we have to do nothing in here. This is not supposed to be move P index and C one step to the right. Okay. Now, is the C, or the current value C, less than or equal to the pivot? In this case, it is also no, because 8 is greater than 4. So we do nothing. So C moves one step to the right. And is the current value C less than or equal to the pivot? Still no, because 5 is greater than 4. So we do nothing again and move C one step to the right. And we now check again, is C less than or equal to the pivot, which is 4? So 3 is indeed less than 4. So what we are going to do is to swap the value of C with the P index. So now this 3 has been transferred to this side, and 7 has been transferred to the 6th index. Okay, and we increment the P index. P index is now here, and similarly, we also increment the C. Now C reaches the pivot, and we are going to swap C with the P index. So C, or the pivot, has now reached its proper na place. Okay, so that's how you perform the quicksort now partitioning. Now, as I said, quicksort is also recursive. So what we are going